University of Waterloo. Today, I'm going to be talking about various congestion control mechanisms. Specifically, we're going to be talking about TCP cubic, LEDBAT, and BBR. So let's get started. So, before I get into the actual talk, we're going to go through an outline of what we'll be covering today. We'll start off by asking the question, what exactly is congestion control? Then, with an understanding of what congestion control is, we will move on to understand the basics of TCP congestion control and the initial mechanism for congestion control that was used when TCP was very young. Next, we'll cover 3 new congestion control mechanisms that provide good support for various use cases. We'll start off by talking about TCP cubic, an extension to TCP that provides support for long-fat networks, abbreviated as LFNs. Then, we'll talk about LEDBAT, or we'll call it LEDBAT, a delay-based congestion control algorithm that uses one-way delay metrics to estimate and utilize all the available bandwidth over a network. Finally, we'll cover BBR, another delay-based congestion control algorithm that utilizes real-time measurements of bottleneck bandwidth along the path and round-trip time of packets to detect any congestion in the network. So, what exactly is congestion control? Well, network congestion normally occurs when the sender overwhelms the network with traffic. Congestion in a network is a state where message traffic in a network is so heavy that it slows down network response times. As a result of congestion in a network, round-trip delays increase, causing performance decreases and potential retransmission of lost packets to occur. For congestion in a network, many algorithms can be employed to handle the congestion effectively and guarantee that all data is delivered reliably. Unlike flow control, where traffic is controlled between the sender and the receiver, determined by the receiver, in congestion control, traffic is controlled when entering the network depending on the network congestion determined by the sender. So let's go through the basics of TCP congestion control and how it started off working. So TCP congestion control techniques will help either to prevent congestion or mitigate it after it occurs. TCP uses something called the congestion window, abbreviated as CWND, maintained by the sender for each TCP session to represent the maximum amount of data that can be sent into a network without being acknowledged. When the TCP flow control sliding window, abbreviated as RWND, is present in the TCP header, the congestion window is not utilized for the data rate determination. Different variations of TCP use different methods to calculate this congestion window. The oldest variant, TCP Tahoe, set the congestion window to one maximum segment size, abbreviated as MSS, and then increases it by 1 MSS every time an ACK packet is received by the sender. This is known as slow start, which results in exponential window size growth. When the slow start threshold is reached, abbreviated as SS thresh, TCP transitions into congestion avoidance. In this state, the window size is increased by 1 maximum segment size over the congestion window size, resulting in a slower linear growth of the congestion window. When congestion is detected through an ACK timeout or duplicate ACKs, the slow start threshold is set to half the congestion window size. The congestion window size is decreased by 1 maximum segment, and then TCP starts over in the slow start phase. However, as our understanding of the internet and its requirements grew, better congestion control mechanisms were introduced. Let's start off by talking about TCP cubic. So what exactly is TCP cubic? TCP cubic is an extension of the normal TCP standard. While it has not been defined as an RFC, the IETF released an official internet draft for it. TCP cubic is a congestion control protocol that modifies a standard linear window growth function to be a cubic one. This improves the scalability of TCP over long-fat networks, where bandwidth delay product, abbreviated as BDP, is very large. Since normal TCP congestion control mechanisms increase their window size based on round-trip time, abbreviated as RTT, TCP does not utilize the bandwidth of networks that have large bandwidth and delay products. The bandwidth is especially underutilized when the length of the TCP communication flow is much shorter than the time it takes TCP to grow its window size to the size of the link's BDP. However, with TCP cubic, RTT bias is completely removed from the equation. TCP cubic is the current default congestion control mechanism in many Linux systems today. And the way TCP cubic works, it allows for TCP to utilize bandwidth properly for applications with small bandwidth limitations and to applications with more long-fat networks, even after reaching the TCP window threshold defined by TCP cubic. This is, for shorthand, the TCP window threshold can be defined as Wmax, and we'll see Wmax in the upcoming slides. So, how does TCP cubic exactly work? Well, when TCP cubic starts off, before any loss event occurs, it registers the congestion maximum window size, Wmax. TCP cubic is a similar, smoother version of TCP BIC, where the window size is represented as a cubic function of time since the last congestion event. Both have a similar shape, but TCP cubic leverages the coincidental benefit of cubic polynomial properties, whereas TCP BIC uses other methods along with binary search. Since it follows a cubic function, there are two different curves associated with window growth. TCP cubic starts off by growing the window size with a fast growth curve on a concave profile, where the slope is large initially and decreases with time until the window size with respect to time reaches the window size of that during the previous congestion event. After this point, when the defined maximum congestion window is passed, the window size initially grows over a convex profile, where the slope is small initially but increases with time until another congestion event is detected. In the convex profile, TCP cubic is constantly probing for more bandwidth capabilities within the link. In the center flat region of the cubic function, TCP spends a lot of time, which allows for the network to stabilize before probing for more bandwidth. Since the second half is a convex profile, links of the long-fat networks will be utilized at a greater bandwidth much faster than other TCP congestion control mechanisms due to the accelerated slope when probing. In TCP cubic, the congestion window is computed using the following formula. C is equal to T minus K to the third power plus Wmax, where K is Wmax times beta over C to the third root. In this equation, C is a scaling constant. T is the time estimated since the last window reduction, time elapsed since the last window reduction, Wmax is window size before the previous reduction, and beta is the multiplicative decrease factor. This formula summarizes how the congestion window is computed with respect to time. So how does TCP exactly handle congestion when it gets it? Packet loss is still the mechanism that's utilized to identify network congestion in TCP cubic, as with other older TCP congestion control mechanisms. When such packet loss is detected through duplicate acts, TCP cubic updates Wmax, CWND, and SSThresh. It first saves the window size at detection as the new Wmax. In other words, Wmax is set to CWND. It then sets the SSThresh to CWND times the beta multiplicative decrease factor. After this step, SSThresh is reset to the max between the computed SSThresh value and 2, due to the requirement of having a threshold of at least 2 MSS. Finally, the CWND is set to the current CWND times the beta multiplicative decrease factor. When packet loss is detected as a result of a timeout, however, TCP cubic still sets SSThresh as defined earlier, but follows the standard TCP procedure to reduce CWND. In this, the congestion window, CWND, is reduced to the value of the restart window, abbreviated RW, which is defined as the minimum between the current congestion window and the initial congestion window, abbreviated as IW, as can be seen in the formula on the slides. Next, we're going to be talking about LEDBAT. We'll call it LEDBAT to keep it simple. So LEDBAT is an acronym for Low Extra Delay Background Transport. It was a delay-based congestion control algorithm invented by Stanislav Shalunov. Although the IETF classifies LEDBAT as an experimental algorithm, it is estimated that about 13 to 20% of internet traffic is carried utilizing LEDBAT congestion control. It is currently being used by Apple to conduct software updates and by BitTorrent for P2P file transfers. The Apple implementation utilizes LEDBAT as a congestion control mechanism for TCP-based communications. The BitTorrent implementation utilizes LEDBAT as the congestion control mechanism for MUTP-based communications. Here, MUTP, which stands for Micro Transport Protocol, is a UDP-based transport protocol utilized by BitTorrent. LEDBAT attempts to use all the available bandwidth on the network while limiting any increase in network delay. Simply put, it does this by measuring one-way delay changes and using those changes to limit congestion, all while attempting to keep the delay as low as possible. So, what are the design goals of LEDBAT? That's what we'll talk about next. Okay, so when we look at the standard TCP congestion control mechanisms, at any bottleneck link, TCP attempts to share the bandwidth equally amongst concurrent flows. However, when we look at internet traffic practically, some applications, such as background applications, are much less sensitive to delay or bandwidth as opposed to other applications, such as foreground applications. This realization led to the need for a congestion control algorithm that takes application delay and bandwidth sensitivities into account. When LEDBAT was first being designed, there were three primary design goals outlined. Firstly, it was to utilize end-to-end available bandwidth in the network and to maintain low queuing delay when no other traffic is present in the network. Secondly, it was to limit added queuing delays induced by concurrent traffic. Lastly, it was to yield quickly to standard TCP flows that share the same bottleneck. LEDBAT is known to react early to any congestion network by using one-way delay to estimate queuing along the data path. So, how does LEDBAT exactly determine congestion? In standard TCP, the congestion window is increased by the sender until a loss occurs or an ECN is received by the sender. Here, ECN is an abbreviation for explicit congestion notification and is an extension to the TCP IP stack defined by RFC 3168 that allows for end-to-end notifications of network congestion without drop packets. ECN occurs only when the queue at the bottleneck link overflows. It is important to note here that any packet loss due to link overflow is normally preceded by an increase in queuing delays on those links. This is the fact that LEDBAT utilizes for its congestion control technique. LEDBAT looks at the increase in queuing delays as early signals of congestion, and since no packet loss occurs in order to detect such congestion, LEDBAT can respond to such congestion earlier than standard TCP. This early detection is also what enables LEDBAT to yield bandwidth to concurrent TCP flows that are more bandwidth and delay sensitive. LEDBAT congestion window computation is based on one-way delay measurements. When the measured delay is less than the target delay, it is assumed that the network is not yet congested, which results in LEDBAT increasing the sending rate to utilize the available bandwidth. When the measured delay is greater than the target delay, it is assumed that the network is becoming congested, which results in LEDBAT decreasing the sending rate in response. Here, as with other congestion control mechanisms, the rate of data transfer is determined by the congestion window, abbreviated as CWND. So we know how LEDBAT determines congestion, but how does it handle congestion? LEDBAT requires that segments be sent with a timestamp in order to compute one-way delay when they arrive at the receiver. These computed delays are sent back to the sender in their corresponding acts. When LEDBAT computes the congestion window, it uses a linear function to determine the rate as a function of the one-way delay. In the equation, the window size is proportional to the difference between the current queuing delay estimate and the target queuing delay. Since LEDBAT increases its window size proportional to the relative difference between the current queuing delay and the target, when LEDBAT is probing for more bandwidth, the rate at which it decreases as it gets closer to the target. The IETF recommends that the target delay be 100 milliseconds or less. To be fair to standard TCP, the rate of the window size increase never surpasses the standard TCP growth rate. And to maintain bandwidth appropriate to different application contexts, when LEDBAT reaches the target delay, it tries to maintain this delay value, where the target delay is set in such a way that it accommodates the application's delay sensitivity. The last congestion control mechanism we'll be talking about is BBR. So what exactly is it? BBR is an acronym for bottleneck bandwidth and round-trip propagation time. It is a congestion control algorithm developed by Google that utilizes real-time bandwidth and round-trip times to estimate estimates to determine the rate of data transfer. This is done by having congestion control mechanisms that decide how fast it wants to send data by considering how fast the network is delivering data. With the data that BBR collects from real-time measurements of network delivery rates and minimum round-trip times, BBR constructs a model to determine how fast it needs to send data in order to maximize the data rate while limiting delay. The best part about BBR is that it is always adjusting this model based on real-time congestion detection measurements. This gives BBR a good view of the network path and overall bottleneck limitations of it, which means it can respond with the appropriate data rate almost instantly. So, why does BBR make sense? Many congestion control algorithms before BBR were primarily loss-based in that the data rate was only adjusted when the bottleneck buffers started overflowing and packets started being dropped. This was okay in the past when TCP came into inception, since at the time, due to expensive memory costs, most routers and switches had buffers the same size as link BDPs. However, as the years progressed and memory became cheaper, buffer sizes increased many folds. And as a result, loss-based congestion control algorithms became efficient in reporting congestion since there was a lot of buffer bloat before the buffer actually started overflowing. This meant that the bottleneck was dropping many packets before the sender was even notified of any such congestion existing. This shows that in today's internet, packet loss is not an effective measure of congestion in a network. BBR, on the other hand, takes into consideration that packet loss can be driven by several external factors not actually related to congestion, and it looks at real-time measurements of round-trip time and the path's bottleneck bandwidth, which results in a much more accurate prediction of congestion in a network. How does BBR handle congestion? To prevent congestion, BBR sends packets at a pace that's equal to the estimated bottleneck rate. This is done with the intention of avoiding network queuing along the path. BBR uses flow adaptation to increase its data rate until it discovers the bottleneck. It periodically spends one round-trip time to send data at a rate that's 1.25 times the current BDP. And if the bandwidth does not change, a queue forms at the bottleneck, resulting in an increased RTT. Detecting this, the sender sends another RTT with data, but at a reduced rate to compensate for this increased RTT. This allows for the queues to be drained and the buffers to go back to being normal. In this process, if the bottleneck bandwidth increases, the sender sends data going forward at this new bottleneck bandwidth rate. The data rate is continuously increased using successive probing operations like the one we just described. When the estimated round-trip time starts to increase, BBR knows congestion exists and assumes the network buffers are filled. Therefore, it maintains this new estimate after one RTT of backoff to drain the queued buffers. In this slide, we can actually see how BBR looks when we visualize it. As you can see, cubic has more the concave profile. Reno just follows a linear growth, whereas we could see BBR probes, goes to a max, comes back to a low to compensate, and maintains the steady state bottleneck bandwidth rate. And BBR has been proven to actually yield the best results when it comes to data transmission rates, and speed of transmission. So the benefits of utilizing BBR are that in 2017, Google actually rolled out BBR as a congestion control algorithm for their cloud platform, replacing the previously employed TCP cubic algorithm. It was recorded by Google that this deployment resulted in higher throughput, lower latency, and an overall better experience for their consumers. Looking at YouTube specifically, when BBR was deployed, YouTube experienced a 4% increase in network throughput. They identified this as a result of better utilization and discovery of the end-to-end network bandwidth provided by BBR. BBR uses round-trip time metrics to keep buffers small through the data path, which directly results in shorter future round-trip times. YouTube themselves experienced a 33% reduction in their average content round-trip times. For some of Google's more delay-sensitive applications, such as Google Stadia, would need to deliver real-time gaming graphics to users that span across various time zones. A congestion control algorithm like BBR that works utilizing round-trip times as a metric while maintaining the goal of reducing such round-trip times provides faster responses and lower delays to such an implementation. Google has reported that BBR provides a mean time between rebuffers that is about 11% higher than previous congestion control algorithms. Additionally, due to the loss prevention abilities of BBR, it is the best mechanism to fully utilize the end-to-end path. This property makes it an ideal match to use with HTTP2, where a single TCP connection is used with multiplexing to make multiple requests. Since HTTP2 allows concurrency on a single connection, and BBR is best at fully utilizing a single connection, together they result in significantly improved internet speeds. To end off, I'd like to say that as the internet has evolved over time, it has come to our understanding as network engineers, old congestion control mechanisms that relied on packet loss were no longer feasible as networks were becoming more complex. TCP cubic helped get better network utilization by probing for bandwidth at a better rate in LFNs. However, it still used packet loss as a congestion detection mechanism. LEDBAT was different in that it was a delay-based algorithm. It focused on maintaining a target delay value and adjusts its data rate based on what the computed one-way delay was. With LEDBAT, bandwidth is used more effectively as congestion is detected with more accuracy while still allowing for standard TCP connections to operate normally. BBR is the newest of the congestion control algorithms we discussed. It uses real-time estimates of bottleneck bandwidth and RTT to determine early congestion in the network. These metrics were decided by Google when implementing it after they analyzed the vast amounts of traffic that was going through the servers. It proved to be the most effective means of congestion detection in today's internet age. It is actually the main congestion control algorithm that's utilized by Google Stadia, providing 4K game streaming to dumb client devices. We can say in conclusion that although packet loss was a good congestion detection mechanism in the past, now real-time estimates and end-to-end throughput and their variations are the best metrics in determining such congestion. BBR dominates this sector in utilizing the most available bandwidth while maintaining the data rate at a constant, which is the maximum that the bottleneck could handle. And that's it for my presentation. I hope you enjoyed it. Here are my references for your reference, and please email me if you have any questions. Thank you so much, and it was a pleasure talking to you. Please have a nice day.